Hello, Calc BC. Welcome to the beginning of our Unit 7. Unit 7 is called Power Series, Taylor Series, and Error. And this will be an expansion of our understanding of series, although we're going to go beyond convergence tests. So that's out of the way. We've learned all of our convergence tests for the year. And in this unit, we are going to explore the idea of putting an X or a variable in a series. So what will happen to a sum? What will happen to a graph of a series if we have an X involved? And as you can see on your screen, we are in the second portion of College Board's Unit 10, Infinite Sequences and Series. Today, we're going to be talking specifically about Taylor polynomials and how those act as approximations of other functions. So this lesson or this unit is going to be 9 lessons. We're going to cut each of these 5 topics from College Board into smaller pieces because there's a lot to unpack. All right. And so today we're going to cover specifically this essential knowledge, although this might not make much sense yet until we cover it. The coefficient of the nth degree term in a Taylor polynomial for a function f centered at x equals a is f at the nth derivative of a over n factorial. You'll see what that means later on. In many cases, as the degree of a Taylor polynomial increases, the nth degree polynomial will approach the original function over some interval. And Taylor polynomials for a function f centered at x equals a can be used to approximate function values of f near x equals a. All right, all of that will become clear as we get through this lesson. And before we officially get to the notes, I'm going to show you a visual on Desmos of what exactly we're talking about here. So give me 1 second to switch over to Desmos. All right, so let's take a look at this graph. This is a graph that we know well. It is y equals cosine of x. And I want to specifically look at this when x equals 0. And when x equals 0, we know we have a y value of 1. So our position is 1 or 0 comma 1. And if I wanted to make a tangent line to this graph at this point right here at 0 comma 1, we know how to do that, right? We know the slope is 0. It's a horizontal slope. And we know the position has to be up at 1. So we could make this y equals 0x plus 1. And this tangent line now shares a position and a slope, or a position and a first derivative with this function, cosine x at x equals 0, right here. But what if we wanted to find, a tangent that was better than this? Instead of just being a tangent line, what if we wanted a tangent curve? What if we wanted a polynomial that shared the position, the first derivative, and the second derivative with y equals cosine x at this point? And what I mean is, I'm going to switch the order of these terms here so we can keep adding more. So it's going to be 1 plus 0x. I'm going to add plus ax squared with the slider for a. So what that's going to do here is add an x squared term where we can change the value of the coefficient using this slider. And I'm just going to move it around until it seems like it matches up best with the graph. Okay, and I think when we set it at negative 0.5, that's the best fit. So it actually means that instead of just being a tangent line that only really matches the graph at that point, now it's starting to take on the look of y equals cosine x for a little bit more of the curve, right? From maybe right around here to right around here. It's a pretty good approximation. And so we can say that that has probably the same position, first derivative, and second derivative as y equals cosine x. And we can add more. So we could say plus bx cubed with a b slider. And now I can slide this around and try to see when does it look the best. And for this specific one, now that we have an x cubed, it's kind of doing that up on one side and down on the other side. thing. And I think actually if we just make b 0, it's the best fit. So the x cubed kind of like had no impact here. So let's keep going. Let's do plus cx to the fourth. And I want to get pretty precise here. So I'm going to change this slider so it just goes from -1 to 1. So I can get pretty precise. And this time we got something good. Look at this. I think if we set this to 0.04, it's the best fit. 2, 3, 4. Okay. Oh. Okay. Yeah. And so now you can see that it matches the cosine curve for even more. It's an even better approximation further out. All because we're centered around x equals 0, and we're trying to match derivatives with the original graph. So now we have, I mean, we're guessing here, but we are guessing that we have the same position, first derivative, second derivative, third derivative, and fourth derivative as cosine x. I'm going to show this algebraically in a minute here, but what we really have is now we have this tangent curve. So instead of just having a linear tangent line, we have what? A degree of 4 tangent curve, all about this x equals 0 on y equals cosine x. And the more terms that we add here to our polynomial, the better this curve will get as an approximation for y equals cosine x. And the idea is that if we keep going infinitely, we'll eventually get a perfect polynomial version of y equals cosine x, which is pretty crazy, but we are going to show that algebraically. We know, let me just connect the pieces a little bit more here. We know that this polynomial can have up to 4 derivatives, because if we take the derivative 4 times, since we have an x to the fourth, we'll still have something that exists. Think about the power rule for derivatives, right? So x to the fourth is going to become x to the third after the first derivative. Then it's going to become x to the second, and then x to the first. And then it'll go away and it'll just be a constant. And then after that, all the other derivatives of this polynomial are just going to be 0, right? Because there are no x terms left. It's just going to be, the fifth derivative of this is just going to be 0. And so on and so on and so on. So that's how we know we're matching up to the fourth derivative with y equals cosine x. If I add another term here and make it x to the fifth, we can get a little bit better. But let's try to algebraically see what on earth is going on here to get this approximation like this. So I'm going to switch over to the notes so we can try that. All right, so here we go. Taylor polynomials part 1, lesson 7.1. Polynomial functions can be used to approximate functions such as sine of x, cosine of x, e to the x, and ln x. And we know a lot more about polynomials than we know about these other functions, right? We've had to kind of memorize very specific rules for taking derivatives, for example, of each one of these other types of functions. But polynomial has very general rules. Polynomials, remember, just mean different x terms with different degrees or different exponents. And we know the power rule is really all you need to be able to take derivatives of those. And we know how to take integrals as well. So we are going to try to match in this preview here. We're going to show the work that we would use to find a polynomial that shares its position and first 4 derivatives with f of x equals cosine x when x equals 0. Now there's a general rule that we're going to use to find a polynomial like this. But first up, we're just going to show all the work. And this might take a little while, but we're going to figure it out. So over here, I'm going to show all the work with the real function that we're interested in, which is f of x equals cosine x. Okay, so let's just kind of think, if we're going to be matching the position and the first 4 derivatives, we're going to need the first 4 derivatives of this function at our disposal. So I'm going to start with just the original function, and I'm going to take the first 4 derivatives. So we're going to need f prime, f double prime, f triple prime. And I will say that after we get to the 3rd derivative, when we write the 4th derivative, it's most common to just put the number derivative in parentheses. And don't get that confused with an exponent, because with this notation, f of x, it wouldn't make any sense to have an exponent right here. So we just put f and then in parentheses a 4, which means the fourth derivative. And if we think about Santa Claus, negative Santa, negative Claus, we can pretty easily get these derivatives, right? The derivative of cosine is negative sine, and then negative cosine, and then positive sine, and positive cosine. But we're not just interested in what those derivatives are. We want to match the position in the first 4 derivatives when x equals 0. So next to this, I'm going to write out, well, maybe below this, I'm going to write out what are these values when x equals 0. So I'm interested in f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and the fourth derivative at 0. And I mean, if we think about our unit circle, we can get these. Cosine of 0 is 1. The negative sine of 0 is 0. Negative cosine will be negative 1, and then 0, and then 1. And that pattern is going to continue, but we're really only interested up to here. So now what we're going to do is try to figure out our polynomial approximation. So I'm going to do that work next door over here. So let's just say we were given this question, given all of these derivatives, find the polynomial that matches. So that's what we're going to try to do. So we are going to say that we know, first of all, I'm going to keep using f, but just for convenience, but we know we're talking about our approximation. We'll make that clear at the end. So I know that the fourth derivative at 0 has to equal 1. So what I'm going to do is just define that fourth derivative of x as 1, because we don't know anything else to say that there are any x's in here. We're just going to make that simple because we're starting at the bottom of the list. We're going to work our way up. So let's take the first derivative, let's take the integral of this and see what happens. So we're going to have the third derivative. It's going to be 1x plus c, right? So let's see if we can figure out what c is using this given information. So I'm going to put all of that work over here. So our third derivative at 0 equals 0. So I know that the third derivative of 0 equals 0 plus c, which is just c. So we have c is 0. So back over here, I could rewrite this as x plus 0. Okay, so we got our third derivative. So let's bump up again. So we're going to go to the second derivative. And now we have x squared times 1/2 plus 0, which doesn't really impact anything. So we'll just say plus c. Our second derivative, when we plug in 0 for x, we should get -1 for y. So I'm going to have the second derivative of 0 equals 1/2 times 0 squared plus c. And that second derivative of 0 was -1. So -1 has to equal 0 plus c. So -1 is c. So back over here, I now have a second derivative that is 1/2 x squared minus 1. So let's keep going. We got 2 more to do, right? Because we have to go up 1 notch to f prime and then up again to f. So f prime of x equals, this is going to become x cubed, and 1/2 I have to divide by 3, so it's going to become 1/6. So I have 1/6 x cubed minus x plus c. If I look back over here, f prime of 0 is 0, so I'm going to plug that in on this side here. Let me just try to make this clear what's going on here. So I have f prime of 0 has to equal 1/6 times 0 cubed minus 0 plus c. All that's going to cancel out and leave me with c, and f prime of 0 is 0. So I have, once again, c is 0. So I have f prime of x equals 1/6 x cubed minus x plus 0. One more step to go. So now I'm going to take the integral one last time to get f of x. And now I have x to the fourth, 1/6 divided by 4 is going to be 1/24. I can subtract x squared times a half. And I have plus 0, which doesn't matter, so plus c. Let's show the work to find c. So we have f of 0 equals 1/24 times 0 to the fourth minus 1/2 times 0 squared plus c. So that all cancels out, leaves me with c, and f of 0 is 1. So I get f of x equals 1/24 x to the fourth minus 1/2 x squared plus 1. Okay, so that is my polynomial approximation for f of x equals cosine x, centered around x equals 0. And this is the exact same equation that we came up with in Desmos a few minutes ago. We figured out that this coefficient was supposed to be negative 0.5, and this one was supposed to be, I think, 0.04. Is that what 1/24 is? Yeah, I mean, it's around 0.04. So that's what we got there. So algebraically, we kind of proved that this polynomial is going to have the same position and first four derivatives as cosine of x. And as we keep adding more terms to this polynomial approximation and keep kind of combining more and more derivatives, this is going to become a better approximation for cosine x. All right, but that was kind of a lot of work. So what I will say is that in general, we don't need to do all of this work every time. There's a formula that will kind of make this a little bit simpler. So I'm going to show you the formula, and I'm going to show you how our approximation fits in with this formula. The definition of an nth degree Taylor polynomial. So a Taylor polynomial is the description that we are going to be using for this kind of polynomial approximation for some other function. You can see here it's named after Brooke Taylor, an English mathematician. So if f has n derivatives at x equals c, so x equals c is going to be where we're centered around. In this first problem, we were centered around x equals 0. Then the polynomial p sub n of x, which means the nth degree Taylor polynomial, is f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared over 2 factorial plus f triple prime of c times x minus c cubed over 3 factorial, etc. That's called, as I said, the nth degree Taylor polynomial for f at c, named after Brooke Taylor. If specifically c equals 0, that's still a type of Taylor polynomial. You can see this is the exact same formula, but 0 is plugged in for c. Okay, so all the x minus c's just became x. All the f of c's became f of 0. This is called the nth degree Maclaurin polynomial for f, named after a Scottish mathematician, Colin Maclaurin. So really what was happening here is that Taylor and Maclaurin were both kind of creating or discovering these types of polynomials independently. So different versions were named after each of them. But a Maclaurin polynomial is a specific type of Taylor polynomial. So they're all Taylor polynomials. We just call them a specific name. So anyway, let's take a look at our approximation and see how it matched up with this, because I'm sure this looks a little bit crazy initially, but it will make sense. So what I'm going to do is kind of rewrite this approximation so that it matches this. So I am going to change it to, first of all, we're going to say this is the fourth degree Taylor polynomial. So it's going to be p sub 4 of x is what we would call this. And you can see the terms in this polynomial start with the degree of 0 and then have x and then have x squared and then have x cubed. So I'm going to kind of reverse the order of how we usually write a polynomial. So it's going to start with 1. And notice there's no x term. The x term canceled out. But to make the pattern clear, I'm going to write the x term anyway. So it's going to be 0x over 1. And then we have the x squared term, which I'm going to write as negative 1x squared over 2 times 1. The x cubed term is missing from our approximation, so it's going to be 0x cubed over 3 times 2 times 1. And then the 4th degree term is here, and I'm going to write it as plus 1x to the 4th over 4 times 3 times 2 times 1. So you can see that for the x squared term, if we kind of combine the negative 1 over 2, we get that negative 1/2. For the x to the 4th term, if we combine 1 over 4 times 3 times 2 times 1, it equals 1 over 24. So I want you to notice a couple things. We had a 4th degree Taylor polynomial. We did 4 derivatives, and we have all the terms up to x to the 4th. You can see that the coefficient in the numerator of each one of these fractions comes straight from the derivatives that we took. So it went 1, 0, negative 1, 0, 1, 1, 0, negative 1, 0, 1. You can also see that in the denominator, we have the same value that was in the exponent and the same value derivative that we took is the factorial in the denominator. So it's 1 factorial, 2 factorial, 3 factorial, 4 factorial. And that comes from the amount of times that we had to integrate to get to this point. So let's think about this x to the 4th term and our work. We started with just a 1. When we made it into an x, we technically divided by 1. We made it into x squared, then we had to divide by 2. We made it into an x cubed, then we had to divide by 3. Then we made it into x to the 4th, and then we had to divide by 4. So that factorial is not just kind of like magically in the denominator of this definition or formula. It's coming from the amount of times we had to integrate an x term to get to that point in our approximation. So now you can see this is the same as the approximation that we found, but we could have got this a lot faster without all of this work if we found the 4 derivatives, plugged them in as the coefficients in the numerators. The denominators are already set for us as the factorials. And then we're done. That's pretty much it. So yeah, hopefully that's starting to click where this comes from. If you kind of read through these definitions again, now that you've seen this, hopefully what this all means kind of makes sense, right? The f of c, f prime of c, f double prime of c, that's the position and then each of the derivatives that we're plugging in. The denominator is just a factorial that kind of is shown here. And then the x minus c is kind of where we're centered. So in the original, we were centered at 0, so we didn't have anything there. It's like a Maclaurin polynomial. I mean, it is a Maclaurin polynomial. So x minus 0 was just x. So all of these terms were just x. But just like with transformations of functions that you've studied, I don't know, all the way back in Algebra 2, we can have like an x minus a certain value inside parentheses to kind of shift this whole thing left or right as needed to get to a different position on the graph that we could be centered around. So let's try that in this first official example of the notes. Suppose that f is a function which has continuous derivatives and that f of 2 equals 3, f prime of 2 equals negative 4, f double prime of 2 equals 7, f triple prime of 2 equals negative 5. Write the Taylor polynomial of degree 3 for f centered at 2. All right, so let's try this. So we are going to start with just kind of listing out the formula. So we're centered at 2. So since we're not centered at 0, this is just going to be a Taylor polynomial, not technically considered a Maclaurin polynomial. I'm going to plug 2 in for all the c's. And we are going to be looking at a degree of 3. So it's going to be p sub 3 of x. And so what we're interested in is f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 times x minus 2 squared over 2 factorial plus f triple prime of 2 times x minus 2 cubed over 3 factorial. And we don't know much about this function, but we know its position and first three derivatives when x equals 2. And that's all we need. I know in the example above, we talked about the specific function cosine of x. Sometimes we're given a specific function that we're finding derivatives of. Sometimes we're not. Sometimes we just have those derivatives. We don't know much else about the function, but we can still find an approximation with a polynomial using this formula for a Taylor polynomial. So now what I'm going to do is actually plug in the f values that were given so we can get a better answer. So we have f of 2 is 3. F prime of 2 is negative 4. So we have negative 4 times x minus 2. F double prime of 2 is 7. And f triple prime of 2 is negative 5. Okay, so what we never, ever, ever want to do is try to kind of distribute to the x minus 2 or kind of foil the x minus 2 and distribute everything. That's going to be crazy. It kind of ruins the beauty of this type of polynomial, and it's never useful. So we are going to leave the x minus 2, the x minus 2 squared, the x minus 2 cubed. What we do sometimes want to do, and what I'll do in this problem, is just kind of like tidy up the coefficients. So that's what I'm going to do for the last step. So we have the third degree Taylor polynomial. That's how we pronounce this. We just say it's the third degree Taylor polynomial. And so we have 3 minus 4 times x minus 2 plus 7 halves times x minus 2 squared minus 5 over 3 times 2 times 1 is 6 times x minus 2 cubed. Okay, and that is a great approximation here. Now, a question that I often get is on the AP exam, if this was a free response question, would I have to actually multiply out the factorials? The answer is no. If you had it written out in this kind of second line that I have here, you have the f's filled in and the factorials are still present, you got the answer. However, just to make it a little bit tidier, if I have extra time, I'm going to kind of actually multiply this out and leave them as coefficients. But, you know, then you're technically prone to error. So I wouldn't necessarily recommend that you do that on an AP exam. But yeah, there we have it. Okay, so that approximation is going to match this function at its position when x equals 2 and its first three derivatives. All right, and we saved ourselves a ton of work. We didn't have to do any of this extra work that we did at the top of the page. So we've got a couple more problems, so let's flip over to the back. Okay, in this next question, we are going to find the Taylor polynomial. We know that means that we're not necessarily centered at x equals 0. We want the degree to be n equals 4. The function that we're modeling after is given this time as f of x equals e to the 3x. And we're at 2. That just means that we're centered at x equals 2. Or in other words, c is 2. C being for center. Okay, so let's try this. So for this one, if we're going to find the fourth degree Taylor polynomial, we need the first 4 derivatives of e to the 3x. So I'm going to have to write out f of x, f prime of x, f double prime of x, f triple prime of x, and f fourth derivative of x. And we're starting with e to the 3x. The first derivative would be e to the 3x times 3. Then we multiply that times 3. Then we multiply that times 3. and then we multiply that times 2. Okay, and then we have to do this when x equals 2. So we're going to take all of these, and now we're going to plug in 2 for x. Okay, and so we have what? When x is 2, we end up with e to the 6th, and then 3 e to the 6th, 9 e to the 6th, 27 e to the 6th, and 81 e to the 6th. Okay, so that's all of the function values that we need. Now we're going to write out the formula. So this is the 4th degree Taylor polynomial, so it's going to be p sub 4 of x. And let's see, I'll start out by just writing it out. So we're going to need f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 x minus 2 squared over 2 factorial plus f triple prime of 2 times x minus 2 cubed over 3 factorial plus x fourth derivative at 2 of x minus 2 to the 4th over 4 factorial. All right, that's what we're trying to fill in here. So let's see what we got. We end up with e to the 6th plus 3 e to the 6th times x minus 2 plus 9 e to the 6th times x minus 2 squared over 2 factorial plus 27 e to the 6th times x minus 2 cubed over 3 factorial plus 81 e to the 6th times x minus 2 to the 4th over 4 factorial. And I am going to simplify that in one final step here. Get e to the 6th, 3e to the 6th, x minus 2. This is going to be 9 halves e to the 6th times x minus 2 squared. 27 over 6 reduces to 9 halves again. And then 81 over 24 reduces to 27 over 8. E to the 6th times x minus 2 to the 4th. All right, so that's the final answer. Pretty crazy stuff, but this is a 4th degree polynomial that models after f of x equals e to the 3x, and it will match at around x equals 2. So what I'm going to do is pause for 1 second, and I want to show you this visually on Desmos. All right, so you can see here that I have graphed y equals e to the 3x. I already typed in our crazy 4th degree Taylor polynomial, and I tried to match the graph so that it would be helpful. So I'm only showing very small values on the x-axis from 0 to 2.5. The y-axis is going all the way from 0 to 200, so we can see the curve here. And if I activate our Taylor polynomial, what you will see is that right around x equals 2, this is going to be a pretty good match for our curve, especially if I scroll up here, you'll see that the blue curve matches the red curve better and better right around x equals 2, which is this vertical line right here. You can see there, it's a pretty good match. They look like they completely overlap. And as I keep going up, it's going to be hard to tell, but the blue curve is not going to match the red curve as good as it did the further I get away. You can see the red and the blue are starting to get away from each other. It's more obvious on the left side where it literally just kind of curves away from the red. If I go back down, yeah, as I get close to 1.5, it's just going to pop back up like that. But right around x equals 2 is where we say we're centered, and that is where we are a good fit. And that's because this polynomial has the exact same position and first 4 derivatives as y equals e to the 3x. So that's why it matches so good, okay? So that's what we're working with here. Let's go back to the notes. All right, we have one more example here with a couple parts. So let's take a look. In part A, we're going to find the Maclaurin polynomial of degree n equals 5 for f of x equals sine of x. So we need the first 5 derivatives of sine of x. So I'm going to list that out over here on the left. I'll have f of x, f prime, f double prime, f triple prime, f fourth derivative, and f fifth derivative. And I know if I'm starting with sine, then I will have cosine, negative sine, negative cosine, back to sine, and then cosine. Notice this said Maclaurin polynomial, so that means we're centered at 0. Remember, that's the specific case of a Taylor polynomial. So now I'm going to list out all of the f's specifically for plugging in 0. Okay, that's a 0. It doesn't really look like it, but it is. And so I'm going to end up with sine of 0 is 0, and then 1, and then 0, and then negative 1, 0, 1. So we've got all of our function values that we need. So we can go straight to the formula. So we are going to have a 5th degree Taylor polynomial. And so I'm going to start with 0 plus 1x plus 0x squared over 2 factorial minus 1x cubed over 3 factorial plus 0x to the 4th over 4 factorial plus 1x to the 5th over 5 factorial. Okay? So once we get better at this, just like I did this time, we don't actually have to write out the formula every single time if we can kind of plug in the derivatives as we go. And let's just kind of simplify this a little bit. We can kind of cancel out all the terms that are 0. So we'll just get x minus 1/6 x cubed, or x cubed over 6, plus x to the 5th over 5 times 4 times 3 times 2 times 1, which is 120. So that is our 5th degree Maclaurin polynomial, which is a special type of Taylor polynomial for f of x equals sine of x. All right, there you go. Very nice. So we're going to use that now in parts B and C. So let's find the 5th degree Taylor polynomial approximation if we plug in 1.4 for x. So what I'm going to do is plug in 1.4 for each of these x's. And I already did this, so I'm just going to write down what I got. But if you type that into your calculator or into Desmos, I'm going to list out all of the decimals here. So our approximation would be 0.9874853. The actual value of f of 1.4 is going to come from sine of x. So if we plug in sine of 1.4, remember that's the actual value. So we end up with 0.985444973. The error in the approximation is the difference between our approximation and the actual value. And so that, in this case, if we subtract these, we end up with 0.0020356. And that error is symbolized by the absolute value of the function minus the approximation, which makes sense, right? That would be the error or the difference between the actual value and our guess. Let's try the same work again for 2.1. So if you plug in 2.1 into our approximation for each of the x's, you're going to end up with a decimal that is about 0.896847175. If we plug 2.1 into sine of x, however, we get 0.86320937. This time the error, if we subtract and take the absolute value, is going to be 0.033633238. So let's compare these. How does the error for 2.1 compare to the error for 1.4? And if we take a look at the errors, the error here in 1.4 is definitely smaller, right? So we could say that the P5 of 2.1 is greater than P5 of 1.4. And if we think about the visual of the graph that we've been looking at a problem after problem in this notes, it should make sense that the further away that we get from where we're centered, the worse the approximation is going to be. So in this question, since we were centered at 0, the approximation at 1.4 is going to be better than the approximation at 2.1 because 2.1 is further away from 0. So what do you think is going to happen if we used our polynomial to estimate the sine of 2.7? Remember, sine is our function that we're approximating here. So if we approximate 2.7, we could say that the P sub 5 of 2.7, or our 5th degree Taylor polynomial, plugging in 2.7, is going to have an even greater amount of error than P sub 5 of 2.1, because we're even further away from where we were centered at x equals 0. All right, so that's kind of what this is trying to get us to think about here. And that is the end of our first section of notes. So thank you so much for watching. I know that this is a brand new concept, so go ahead and try the worksheet and let me know if you have any questions. Thank you so much. Have a great day.